Okay, welcome back, static students. This is the third recorded lecture on trusses. And again, this is BTC's ENGR 214 ampersand winter 2020. And the subject of this lecture is truss shortcuts. We just had two examples on the method of joints, and we now have an appreciation for how bomb-proof but somewhat cumbersome that is, and how many steps it takes to do it right. In fact, do it at all. And that's probably one of the downfalls of the method of joints, is that if you want to get the force in just one member, say, not solve the whole truss, you pretty much, very likely, get to guaranteed get it, you're going to have to solve the whole truss. So given that we've got a lot of work to do, let's look to see if there's any shortcuts that we can deploy safely that are not going to lead to us getting the wrong answer, but might shorten our timeline to getting the right answer. And one of the most potent of these is what's called a zero force member. So this is defined as a truss member which cannot carry load. Not doesn't happen to carry a load, cannot carry a load, because if it did, it would accelerate, or something else would accelerate. So if you put load in that member, you cannot meet the conditions of equilibrium at one or more joints. That's the definition. So if you can spot a member and be sure that it is a zero force member, you can just take it out of your FBDs. You can just not include it. Now, I hope you recognize the obvious danger to this. If you think something's a zero force member, maybe because you drew it in such a way that suggested it was, but it turns out not to be, and you take it out of your analysis, everything else will be very wrong. So be very, very sure. So what's one way we can be sure? Well, first of all, a zero force member is going to end on pins, at least one pin, that doesn't have a force. So if I look at member DE here, DE ends on pin D and pin E. There is an external force at both of those pins, which means it's possible for DE to carry load. Candidates for being a zero force member, AE only, because every other one of these members ends on either a support reaction, which is going to be carrying some kind of load, especially because this is a simply supported truss, or where we have a directly applied external load. AE, on the other hand, has point A, which doesn't have an applied load. Now, just because you're ending on a joint that doesn't have an applied external load or support reaction, which is an external load, doesn't mean it's a zero force member. We then have to go the other step and say, could we write equations of equilibrium for that joint and show that if that member carried any force at all, it would be impossible to satisfy the conditions of equilibrium. And if we look at the case of AE, we can at least eyeball that and show that it's true, because basically the members CA and AD are collinear. So they can only apply load in their direction of orientation, and AE is coming in with a component or a significant component that's perpendicular to that. So there is nothing in forces AD and AC that can necessarily oppose all the components of AE, particularly their horizontal components. It's going to be unbalanced. So if AE carries a load, we cannot put pin A into static equilibrium. We could go ahead and write there and show it rigorously, but if we did that, we might as well just include it in the method of joints and just show that it ends up being zero. So we can recognize this just because it's coming in perpendicular or close to two other members that are collinear going through a joint that has no other loads applied. So AE is a zero force member. So we could simply remove it from the truss, do the analysis, and we'd get the right answer in all the other joints. Okay, another shortcut, less powerful but might save some time. A four-member pin. So if you have a pin and you've got four different members going through, and especially if they're all in tension, it's easy to see that they'll almost act like a continuous member. And so we can say that FA1 is equal to FA2, FB1 is equal to FB2. So they kind of reflect across. Again, you could go and show this rigorously if you wanted. The point of the shortcuts is to see it and then be able to apply it without necessarily having to rigorously apply the equations of equilibrium. And I'm speaking with so much caution because remember, if you apply one of these wrong, your entire solution will be wrong. In a default, you can always drop back to the straight up method of joints or method of sections that we'll get to later and always get the right answer. So these shortcuts should be used very, very judiciously. The final one is what's called a non-collinear member. And again, this is one where you can see that if there are any external forces applied at a given pin, then the forces in all the members going through that pin have to be zero. And again, it's because there is no way that they can carry load that would be opposed by a load in the other member going through that pin that would balance it. So you can see members CB and BA can't carry load without there being some component of the force in one or the other that isn't opposed. So both CB and BA have to be zero force members in order to put B into static equilibrium. So this often happens when you have a pin that just has two members and they're not collinear. So that's a bit similar to the rationale here for the four-member pin where the collinear members have to have the same load. So three shortcuts: zero force members, four-member pins, non-collinear members. None of them can carry load because if they do, the pins where they join cannot be put into static equilibrium. So let's go to an example where we can deploy that. So this is example 4.3. We have a cantilevered truss. These are kind of exciting. And in this case we have two hinges. So rather than having one of these only apply force or only be capable of applying a force in one direction, both A and G can apply force in two directions. So each one can apply a vertical and a horizontal force. We've got 1, 2, 3 applied loads, and we've got a whole bunch of members here. So we're going to be looking for shortcuts that will help us out, and I hope you can start taking a look. If you wanted to just go through and say, now that I know what the shortcuts are, I'm going to start browsing for them. I could say, hey, maybe point D is that non-collinear. But no, I've got an applied load, so that isn't going to work. Well, CE might be a zero force member. Look, it's ending perpendicular to the line made by BC and CD, but I've got an external load, so that sure isn't going to work. This is a pretty standard joint. This is a pretty standard joint, but I might want to take a look here at pin F. I have member BF coming in. There's no external loads being applied at pin F. So there's really no way for any kind of load in GF, which is totally horizontal, or FE, which is totally horizontal, to oppose a tensile or compressive force in the totally vertical BF. So if BF has any load at all in it, pin F will accelerate up or down. So I know BF is a zero force member. So I just took one of these members out of my analysis, which is nice because I have quite a few analyzed. Okay, thinking ahead towards that, we'll just kind of go back to, I've made one shortcut, but a lot of other members to solve for that I can't remove. So let's go back to our standard method of whole truss to get the support reactions. And this time I got 4. So I may or may not be able to get them all with my whole truss FBD. And in fact, I know for darn sure I can only get 3 of the 4 because I only got 3 equations of equilibrium, right? So I will draw my whole truss FBD. I have the support reactions at point A represented here, A sub x and A sub y. I've chosen to draw the support reactions at G with the horizontal force in the opposing direction, just because those are the only 2 horizontal forces in the truss, so I know they got to be going different ways. They may be opposite of the way I've drawn, but I know they have to be in opposition to each other. And I've chosen to draw G sub y in the vertical direction. We don't know if it will end up that way. I'm using the 2-meter lengths of members A, B, B, C, and C, D to position my 3 applied vertical loads. So I can write my equations of equilibrium for the whole truss. Sum of the forces in the x is 0. So A sub x is equal to G sub x, which I kind of did deliberately. Sum of the forces in the y is 0. So I have A sub y going up, G sub y going up, and that is being opposed by 3 plus 5 is 8 plus 6 is 14 kilonewtons downward. So A sub y plus G sub y equals 14 kilonewtons. So now I'm going to deploy my moment equation, and I'm going to take the sum of the moments about point A. So that means I'm going to remove A sub x and A sub y and G sub y from the equations of equilibrium, from this equation anyway. There's still in other equations of equilibrium, sorry. And so I will have G sub x at a radius of 1.5 applying a positive moment, and then that's opposing the negative moment about point A from all 3 of my applied loads at their respective 2-meter, 4-meter, and 6-meter radii from point A. And everything's perpendicular, so I don't have to worry about signs of angles between or taking cross products. So the moment about A drops out my support reaction G sub x. So I have 41.33 kilonewtons, and it happens to be in the direction shown, which immediately gives me A sub x and leaves A sub y and G sub y related to one another, but no independent solution for either one. So I'm going to have to get, I'm going to have to write one in terms of the other, solve for it with my method of joints, my joint equilibrium, and my other forces at points A and G, and get that later on, which is fine. We will have plenty of equations. So step 2, look for shortcuts. We kind of did that before we did our whole body FBD. Look for 0 force members. We found one. 4 paired members, no. Non-collinear, no. And so we can take a look at member CE here. We checked that out to see if it was a 2 force member, and found that it could have been if we didn't have an applied load there, but we do, so it's not. We gave it the hairy eyeball. Okay, so now we're ready to dive into our method of joints. And so this is going to be a long haul because we've got a lot of members and a lot of joints, and we want to solve the whole truss. So now we're back to exactly the same method that we did in our 2 examples previous. And just to orient myself, I've chosen to start out at the end, at point D. You can see at point D, I've got 2 members coming in. Every one of my 2-dimensional method of joints equilibrium analyses is going to give me 2 equations, so I know I can get both members at D. So I can cascade that back in, maybe save myself some math. So I have my 6 kilonewton externally applied load in the vertical. I've chosen to represent CD as having a tensile force. It's pure horizontal. And I have DE coming in at an angle theta, which I had to get from my geometry. I have 1.5 here between points A and G, so that's the same as between points C and E, and then 2 meters. And so that gives me my angle theta. Basically, it would give me this angle. So subtract 90. A tan of 2 meters over 1.5 meters. So this angle is 53 degrees. So I apply some of the forces in the X and the Y. I have X components, sine theta times dE minus CD is 0. And then I have cosine theta, dE opposing 6 kilonewtons. That gives me dE plug it back in here. That gives me CE, and I end up showing that member DE is carrying 10 kilonewtons and it's in compression, and then CD is carrying 8 kilonewtons and it's in tension. So I guessed right on directions. So moving over to pin C, so let's just go back and look where that was. So I'm moving one spot over to the left, pin C. So now I've got 1, 2, 3 members coming in. I already know CD. I got one externally applied load, so I should be able to get the forces in members BC and CE with my one equation of equilibrium, if I do it correctly. All the members are coming in orthogonally and aligned with the coordinate axes, so this is pretty easy. I have my 10 kilonewton applied load. I have 8 kilonewtons in tension that I saw for back at the previous pin, at pin D. So if it's in tension, it's pulling. And I used the fact that I have 5 kilonewtons coming in vertically. I only have one member to oppose it. So I actually did a very quick sum of the forces in the Y without actually writing it out. And I assigned member, having to go back and forth and look, CE. Member CE is the only one that can oppose that 5 kilonewton applied load. So it's carrying the entire applied load. So that forces it to be in compression. So the pin is being pushed up by member CE, and so it's being pushed back on. It's in compression. So that leaves member BC to oppose our 8 kilonewton load, and that means it has to be in tension. So now I have CE and BC. So I'm going to move to pin E down here, and I now know the load in CE was 5 kilonewtons. I have my load in DE from my my analysis of pin D. So if I put pin E in static equilibrium with this load known and that load known, I can get these two. So I can get it with one equation. So we'll take a look at how we did that. Now we have things coming in at angles. DE is coming in again at angle phi. This is defined as 36.8. I'm using the geometry of the truss. I have 5 kilonewtons of compression coming down from CE, which I solved for in the previous FBD of pin C. And I'm going to choose to represent BE as being in tension and FE as being in compression. Run through my equations of equilibrium, sum of the forces in the X. I'm going to have member FE in compression pushing to the right. That's the positive X direction. Minus BE cosine phi minus DE cosine phi, but I know that DE is 10 kilonewtons. Sum that up. I got two unknowns. So I'll turn to my equations of equilibrium in the Y. Write those out. So I have a BE sine phi minus 5 kilonewtons minus DE sine phi, and I know DE is 10 kilonewtons. So it's only one variable. So I can get force in member BE is 18.33 kilonewtons. It's in tension. And I can plug that back in here and get my requisite amount in FE, which is compression. So notice this was positive, that's positive. That means the direction I drew it in right here in the little method of joints FBD of pin E was correct. And so we have BE in tension and FE in compression. Okay, moving on to pin F. Let's see what we'll get there. Aha! Here's where we have our zero force member. This is great. So we don't really have any force vertical in F. We know what the force is in member EF. It's in compression, so we know that GF has to also be in compression pushing back. So GF was a bit of a gimme. So we can just confirm that. So if I do an FBD of pin F, I represent the zero force member as having 0 kilonewtons. I have 22.66 kilonewtons coming in from member FE, which is in compression, so it's pushing on pin F, and that means GF has to be pushing on pin F, which means pin F is pushing back on GF, which means GF is in compression, and it's got the same magnitude as EF. So 22.66 kilonewtons compression. Okay, what we're going to do next? Now we move up to pin B. So do we have enough? We've got an external load. We have no force here. We've already solved for BE. We've already solved for BC. So that leaves two unknown members. We have two equations of equilibrium. So we should be able to knock out the last two members with just our equations of equilibrium of joint B. That will allow us to get the force in member GB. We already have just solved for the force in member GF. That will give us our remaining support reaction that we weren't able to solve for. And then we can plug whatever we get for GY back in and get AY. So pin B is going to give us quite a bit. And then either one of these two support pins will give us the solution for both the Y components of the remaining supports, and whatever one we don't use will be our final check. So, all important pin B. So let's make sure we've got this correct. We're picking up 8 kilonewtons from an already solved member, 18.33 from an already solved member. Both of those happen to be in tension. We have our unknown AB in the horizontal and our unknown BG coming in at the same angle. These are both angles of theta, which are 53 degrees from the truss geometry, applied downward load of 3 kilonewtons. So we're going to tally up an X. We have 8 kilonewtons positive plus 18.33 sine theta in the positive. Also in the positive BG sine theta, because we have it in compression, so that means its horizontal component is pushing to the right, which is in the positive direction. And all of that being opposed by all of AB, which is horizontally oriented. So we do our same tally up in the Y. We now have the Y component of BG, which is BG cosine theta upward. We have 18.33 kilonewtons cosine theta downward, and then 3 kilonewtons downward. So this equation will give us BG, and it ends up being 23.33 kilonewtons in the direction shown. It's being shown in compression. It's being shown pushing on the pin. Pin pushes back. When something's pushing back on you, you're in compression. BG is in compression. Plug that value in as a positive number in the direction shown into this equation of equilibrium, or X, and that will give us AB, which ends up being 41.33 kilonewtons in the direction shown, which is a tensile direction. So we have those two. And we're going to reserve pin A as a check. Its X component. So remember, we had already solved for the X component at pin A way back in our support reactions. A sub X equals G sub X. We were able to get G sub X as the moment, and so we were able to show that A sub X was pulling, that support reaction was pulling on the truss with 41.33 kilonewtons. So A is pulling, the support hinge is pulling on point A. So we better hope that AB was tension. So, and it was. So we have our first check. We have now checked the horizontal component of our truss against the one horizontal support reaction that we had available there. So now we need to apply what we had just solved for in member BG to get our Y component of our G sub Y support reaction. And we'll also pick up an X check. So we use G sub Y. We do an FBD of pin G down at the lower support reaction. And we solve for G sub Y equaling what we just had solved for. And remember coming in here, remember the name? BG. So BG sine theta So the y component is going to balance g sub y. That gives us a g sub y of 14 kilonewtons upward. So that means, going back to our whole truss FBD, that means g sub y is pushing in the direction shown. So it's pushing up, so that hinge is pushing up on pin G. So if I go back here and I plug in that 14 kilonewtons, I find that A sub y is 0. So the hinge at A isn't applying any upward force. This upper area is an X only. It could apply a force in the Y. If we changed any one of these applied loads here, it might need to. But as loaded now, it doesn't have to. Just because you can apply a support reaction doesn't mean you will. But you have to allow for the possibility, so you have to solve for it. And we also get a check here with our X component, already knowing what our G sub X is. Again, having solved for that way up in our very first support reaction from our moment equation. This is our 41.33 kilonewtons that we solve for from our support reaction using the sum of the moments at point A. We know it's pushing on pin G kind of as a compressive member, pushing to the right. And if we take the X component here, and then the other horizontal load carrying over, those do indeed sum to 41.33, and that provides our final check. So we have solved our truss support reactions, all four, one of which ends up being 0, and all of the forces in our members, including the one which was a zero force member. So that is it for this lecture. We've now gone through an example of a truss shortcut and done a nice reinforcement of the method of joints. Next topic, we will move on to looking at truss solvability. So we'll start applying very rigorously our number of equations and unknowns with respect to the number of pins, the number of support reactions, and the number of members, so we can decide whether or not it's worth jumping into an analysis right from the get-go, or whether we can tell somebody, oh, nope, sorry, your truss is going to accelerate, or it's overconstrained. I can't give you a single unique solution. I may be able to give you some members, but some will just be written in terms of others. In other words, there might be an infinite number of solutions. So we'll be able to tell that just by counting, and so we'll do a little bit of math and get set up in terms of that so we can identify things faster. And then when we're done with that, we will be ready to jump into the method of sections, which is basically the second big method used for truss analysis. And it is especially useful if you only need to know the force in one or two members and don't need to solve the whole truss. So we'll talk to you then.